And exercise 2 says to find the intervals on which this function is increasing and when is it decreasing, and locate where the tangent line is horizontal. In other words, where is the function at a maximum or a minimum, okay? And then graph the function itself without using your calculator to graph it is what they're implying. Don't use your calculator to graph it. So what we want, and I'm not going to graph the function, we were looking at a table last time and just basically scrolling up and down in the function. So I'm going to try to get this table back to 0 so that we can go backwards and forwards from there. And this is the graph of the derivative. This is the graph of the derivative, not of the function. It's the graph of the derivative. So here's what we want to do. It's the table of the derivative, and also we're going to look at the graph of the derivative, not of the function itself. And because we've got graphing calculators, you don't really need any more to be able to use derivatives to help you find the graph of a function. That was back in the dark ages when I was an undergraduate. But the reason I'm going to look at this a little bit now is because in chapter 15 we're going to be given the graph of the derivative or the equation of the derivative and have to figure out what the function was. So from that standpoint, this is going to have value. We're not really so much interested in using this as a graphing technique. So what we've got here is we've got a bunch of values. And what I want to do is I want to create a number line. And look at intervals where the function is increasing and decreasing based on its derivative. So we're going to look at where is the derivative positive and where is it negative, and then we're also going to think about what happens in the places where it shifts from positive to negative. So starting here at 0, remember that this table says that at the value 1, the derivative's value is, for all intents and purposes, pretty close to 0. 1 e negative 6 is pretty close to 0. So at the value x is equal to 1, we're figuring that the derivative's value is 0. Okay? And then what we notice is that when it gets to 2, it's positive, and it becomes increasingly more and more positive. So after we go past 1 to 2 and on to, it appears to be infinity, the derivative itself then is positive. Which means our function is increasing. And we'll scroll a little bit so that you see that it doesn't change directions, it doesn't come back down, it continues to go on up. Now, if you remember from finite mathematics, this is a cubic equation. So how many turning points does this equation have? It has 3. It's either going to go up, down, and back up, or it's going to go down, up, and back down, one or the other. Okay? And it appears to be going on up, and that's one of the turning points. So that's justification for us to realize that as I keep on scrolling down, let x get bigger and bigger and bigger, then the value of the derivative is going to continue to be positive, and it's going to be increasingly steep. And what's happening here is that f of x has a turning point. Right now, that's all I'm going to call it, is a turning point. I'm not going to call it a maximum or a minimum just yet. Okay? So now I'm going to go back where we started from. Let's see, I think Travis is having a hard time seeing from there, so let me put it in the middle, because I'm sure if you're having a hard time, Caleb is too. Okay, and so what I see happening here is that when it went to 0, the derivative is negative. Remember, I'm looking at the values of the derivative, not the graph. So I see that at x equals 0, the derivative is negative. And it continues to be negative as it goes toward -2 until it gets to -3. And then it does something different at -3. So the behavior from -3 to 0, let's say, at the value 0 it's negative, at the value -1 it's negative, at the value -2 it's negative, but look up here at -3. It's basically saying it's back to 0. The derivative's value right there is 0. So here's what's happened. On this interval, from -3 to 1, it's decreasing. And that's because its derivative is negative, which tells us it has a negative slope. So the function is decreasing because it has a negative slope. Okay? But when we get to x equals -3, the function has reached another turning point. So then we go on below x equals -3 toward -infinity, and notice the derivative becomes positive again. And it becomes increasingly positive. It gets larger and larger and larger and more positive. So the derivative again now, as we go toward, this was toward positive infinity, and on this end we're going toward -infinity. And as we keep going toward -infinity, now the derivative is positive. Okay? So looking at it strictly from a numerical standpoint, here's what we see is happening. This function on the interval -infinity to -3 is increasing. But it reaches a maximum when it gets to -3. So this turning point here is a maximum. And then it starts to decrease until it gets to 1, and it becomes 0 again, which tells me there's another turning point at 1. So there's another turning point. And the fact that it's decreasing until it gets there. But then once I get past 1, it starts having a positive slope again, which tells me it's going to travel back uphill. And it's going to keep traveling up forever and down forever on those two ends. And then here are your turning points. That was the maximum, and this is going to be a minimum. And if you think about it, that makes sense, because when you go from positive to negative, you have reached a maximum. And when your slope goes from being negative to being positive, then you have reached a minimum. And that's consistent with what we know about this kind of function. We know that a cubic function has two turning points, that its end behavior is that as it approaches negative infinity, its function values approach negative infinity, and as the function approaches positive infinity, then its function values approach positive infinity. And the only other thing we need to know is that it has a y-intercept of 10, so this point right here would be 0, 10. The other ones, I would have to do a little figuring to figure out exactly what the value of the function is, but it wouldn't be hard. I could find the y value here by knowing that I'm going to plug in -3 and get the y partner to that point. And here I can plug in 1 and I can find the value of the function, the y value at x equals -1 right here. So I could draw a really accurate graph by being able to do that. So remember, this is in the days before graphing calculators, like I said, back in the dark ages. Okay? So this is the graph of the function. Even though it's not perfectly accurate, I could draw a really accurate graph with my algebra skills and some calculus without needing a graphing calculator. But again, the key is when the slope is positive, your function's increasing. When your slope is negative, your function's decreasing. When your function when your derivative has a 0, then that means that your function has reached a maximum point or a minimum point. Okay? These are called the critical points. Those are your two critical points. Critical points are where your function either has a maximum or has a minimum. And it is also possible to have a critical point where it's neither a max nor a min. It might be an inflection point. Okay? So this is just a summary of everything that we've just said. And you can find the derivative of the function and then factor it, which is what I've done here. So the derivative of x to the third, and by the way, on your handout there's a negative sign that's not supposed to be there, so scratch out that negative sign. It's actually supposed to be x cubed plus 3x squared minus 9x plus 4. And I'm pretty sure that's what I've got in my calculator. I hope so. Yeah. So the actual function doesn't have a negative sign in front of it. And once I've got its derivative, 3x squared plus 6x minus 9, I can actually factor out the 3, and then factor x squared plus 2x minus 3 into x plus 3 and x minus 1, and guess what? That's the critical values. So algebraically, you could have found the critical values without doing it numerically like I did. Okay? That's why part of your skills review for this chapter included a review of factoring, because sometimes it's helpful to be able to find your zeros of your function by factoring. So this is the sines graph that we just made. And these test points that it's referring to are simply telling you plug these numbers into the derivative to determine whether the derivative is positive or negative at that point. But I figured it was easier to actually let the calculator find the derivative and then use the table to do that arithmetic for us, so I didn't make you do the arithmetic. So the graph of x cubed plus 3x squared minus 9x plus 4 does look like this. And mine, I think I have a typo. Mine says plus 10. Yeah, but it's supposed to be plus 4, so you might want to change that plus 10 out there to a 4. I need to fix my handouts. So change the 10 on your handout to a 4. So there's what the graph looks like, and we drew the graph without knowing any of this. So for practice 2, we're going to do the same thing. And we've got practice 2 down here in front of us. Let me make sure I copied this one down right. Oh, practice 2 is the one that you have. I'm sorry. Practice 2 is the one that you have. I was thinking it was example 2, but it's practice 2. So let's work practice 2. My extra paper go. So for practice 2, here's what we had. Let me write it down first, then I'll switch. So we'll go through one more time to make sure we know what we're doing. This is the function. We want to graph it, but we don't want to use the graphing calculator. We're going to try to do it using the critical values. So the first thing we're going to do is we're going to take its derivative. And that's going to be negative 3x squared minus 4x plus 15. And I'm going to factor out a -1 because I don't like to deal with negative leading coefficients. And I could factor this 2 or 3 different ways. If it has integer factors, I can set this equal to 0 and find the places that there are zeros using the quadratic formula. So if I use a equals 3, b equals 4, c equals -15, the opposite of b plus or minus the square root of b squared minus 4ac over 2a. You should recognize that from finite. And I'll just plug in. X is equal to -4 plus or minus the square root of 4 squared minus 4 times 3 times -15. All divided by 2 times 3. X equals -4 plus or minus the square root of, let's see, that's 16. 3 times -15 is -45, and -45 times 4. I don't feel like doing arithmetic in my head. We'll do it on calculator.
-180.
-180, thank you. And since it's -4, minus times minus makes that plus 180. So that's going to be the square root of 196 over 6. And the square root of 196 is 16? 14? I heard 14 or 16? 14. Okay. -4 plus or minus 14 over 6. -4 plus 14 is 10. -4 minus 14 is -18 over 6. So the derivative is equal to 0 when x is either 10 over 6 or 5 over 3 or 1 2/3. Don't make a decimal because it's not a terminating decimal. And when x is equal to -3. So f prime of x is equal to 0 for x equals -3 and x equals 1 2/3 or 1.67. Since we're only going to locate it on a number line, we really could just change it into a decimal, I guess. So then y'all can start feeling sorry for me now because this is the way I had to do all these graphs. No graphing calculator. I get a number line and I plot on that number line the value x equals -3, the value x equals 1 2/3, And then I'm going to test values in both intervals. So in this interval, I will test -4. And in this interval, I will test +3. And in this interval, I'm lazy. I'm going to test 0 to see what happens with the derivative at those points. So this time I'm really going to do it the hard way. So -3 times -4 raised to the second power minus 4 times -4 plus 15 tells me that the derivative is negative on this interval. So for all the x values less than -3, the derivative is going to be negative. Until it gets to 3, then it's going to be 0. And then I bet when I plug in zeros in place of those -4s, it's going to be positive. In fact, I know it is, because 0 plugged in there is going to make that disappear, going to make that disappear, and all I'm going to have is 15. So it's going to be positive on this interval until I get to the next critical number, 1 2/3. And then I'm going to plug in 3 and verify that it's going to go back to being negative. And it does. So at this interval, my derivative is negative, 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 negative. So if I'm going to graph this function, here's what I know. It's going to have a y-intercept of 0, 10. It's going to start out having a negative slope, which means it's going to go down until it gets to -3. Then it's going to change at -3. It's going to go up until it gets to 1 2/3. Then it's going to change again, and it's going to go down. And from that, I can sketch a graph. Let's see, a convenient place to do that. Doesn't matter if it's a very big graph. So it's going to go down until it gets to -3. It's going to change. It's going to have a y-intercept at 10, and it's going to go up until it gets just barely past the x-axis at 1 2/3, and it's going to go down again. So there's what that graph's going to look like. So now I'll let my calculator verify it for me. So -3x to the third minus 2x squared plus 15x plus 10. And I don't have to see its derivative. I just want to see the graph and see if I'm right. So I'll put it on my standard window and hit graph. And the graph does look sort of like what I expected it to, but apparently I need to increase my y values. My max and my min need to be bigger. And it's still a little bit bigger. So it does exactly like we thought it would. Okay? Now, this really, except for the fact you're taking derivatives and looking when the derivative is positive and negative, this is really not a calculus idea other than trying to get you to remember that what a derivative tells you is the slope of the original function, which will tell you when it's increasing and when it's decreasing. So there's the graph that we came out with. And there's a lot of other algebra that you can do to go along with that, but all we wanted was a sketch of the graph. And we can do the same thing with example 3, but I'm not going to belabor this point. That's not something I'm really interested in doing in chapter 13, because most of the time what we're really going to do is we're going to look at the graphing calculator and get our graphs. So we're going to find f prime, and actually I found f prime by graphing it. So 2x plus 4, close the parentheses, delete all the rest of that stuff, and raise it to the power of 2/3. And then I'm going to graph not the function itself, but the derivative of the function. And I probably need to fix my window because that looks pretty terrible, so. So here's my derivative, not the function itself, but the derivative. And I'll see if I can get it to eliminate where it's trying to connect up the function. Now it's on dot mode, it shouldn't be connecting it anyway. Let's try this. Okay, there we go. So here's what the derivative looks like. It looks like there's something odd going on here at -2. Why would there be something odd going on at -2? Looking at the original function, why would -2 be a problem in the original function? It's going to make that part inside parentheses 0. And if you raise 0 to the 2/3 power, it's still, guess what, 0. So at that point, the function itself has a 0, or there's something going on with the function. The derivative apparently is negative until you get to -2, until you get to the value of -2, and then it becomes positive. So that find f prime and set it equal to 0 to find the critical numbers, but here's the issue. Right there seems to be the only place that f prime is equal to 0, and that is at 0. So when we actually graph the function and not the derivative, we're going to see that it sort of does remind you of the derivative. And the derivative is graphing right here along with it. So here comes the derivative. It's negative, and the function's decreasing. And then it's positive, and the function was increasing at that particular -2 value. So what it tells you is that the function went to 0 at that value and then started increasing. It decreased, it hit a root, and then it increased. So where the derivative was trying to be equal to -2, there was a critical point going on in the function, a place where you couldn't take its derivative. Because you can take the derivative of this function there and there. The only place you cannot take the derivative of that function is at -2. It creates a problem. You can't take the derivative there. And the derivative was showing you that it wasn't defined at -2. So once again, this is just about connections. I will caution you, the test for increasing and decreasing, when we were looking at turning points, the function has a turning point when its slope goes from negative to positive, or from positive to negative. It has a turning point. Don't assume that just because the derivative hit 0 that the function itself went from positive to negative. It doesn't necessarily have to do that. And here's one for you to consider. Here the derivative is positive, has a 0 point, and then goes back to being positive. So f of x equals x cubed is positive for its whole domain. It's increasing throughout its entire domain. And yet it has a critical value at x equals 0, because that's where its derivative is equal to 0. The derivative of x cubed is 3x squared, which is 0 at value x equals 0. But the reason for that is not because this is a minimum or maximum point on that function. It's an inflection point, okay? Which is actually going to lead us to needing another test to find out when we have inflection points. Because just knowing where turning points are isn't enough. You have to know where inflection points are too. So we'll also have something called the second derivative test in the next section. So the last problem we're going to do is going to deal with profit analysis. Company selling computers finds that the cost per computer decreases linearly with the number sold monthly. It decreases from $1,000 when none are sold to $800 when 1,000 are sold. And it's linear decrease, so that means it's a constant decrease. So the average cost function has a y-intercept of 0, 1,000, because when you do C of x over x and plug in 0, you're going to get 1,000. And it has a slope of -200 over 1,000 because the decrease in price from 0 to 1,000 is down $200. So that is a -0.2. Here's your average cost function. Your average cost function has a slope because it told you it decreases linearly. So it has a slope of -0.2x, and its y-intercept, in other words, where you don't sell any, that's going to be 1,000. And it's a cost function, so that's in dollars. And this is only applicable when x is between 0 and 1,000 because it specifies that. So your cost function is C of x, which is x times the average cost function. X is the number of computers. And this is the average cost per computer. So that means it's going to be x times -0.2x plus 1,000, which means that your cost function is actually quadratic. And it opens downward because it has a negative leading coefficient. So what that tells you about the cost function is that the cost is going to increase unto a certain point, and then it's going to start decreasing again. And then they give you the revenue function, and I do have a typo in that. That's supposed to be a decimal, not a comma. So it's 0.008x to the third is the revenue function, minus 2.4x squared is the second term, and then plus 2400x. So this is the amount of money you make for selling X computers for the first 1,000. And now they want to talk about profit. How do you find profit? If you've got a cost function, you've got a revenue function. How do you find profit? Revenue minus cost. Okay, what do you hope about your profit function? You hope it's going to stay positive. Is it always going to stay positive? Nope. At some point it's going to be negative. What does that mean about your profit? You're losing money. Okay? So let's think about this. Get the calculator. Turn it on. Go to y equals, clear those out. I've got a cost function. I have an average cost function, which is negative 0.2x plus 1,000 per computer. So if I sell X computers, then I'll multiply X times that cost function. I'm sorry, times the average cost function, not the cost function. So there's my cost equation. And then my revenue equation is 8 thousandths times X raised to the third power minus 2.4 X raised to the second power plus 2400 X, and that's the revenue from selling X computers. So actually your average revenue you could find by dividing an X out of all of these, and your average revenue is 0.008X squared minus 2.4X plus 2400 for your average revenue. So I've got cost, I've got revenue. What I want is profit. And profit is revenue, which is Y2, minus cost, which is Y1. And notice I don't even have to do the algebraic expression for it. I just want to look at its graph for the time being. And the only one I want to graph actually is the profit function right now. And it says X needs to stay between 0 and 1,000, so I'll use that to set my window. So 0 to 1,000, zoom, fit. We'll let it pick the Y coordinates so we can see what the profit function looks like. What does that graph tell me about my profit function? It's constantly increasing. Where's my maximum profit going to be? When I make the 1,000. Okay? Now think about why that might be true. Your average cost function is linear. Linear increases at a constant rate. Okay? Your revenue function and your cost functions, revenue is cubic, cost is quadratic. So that means that your profit function has a curve. It isn't straight. The interval where profit is increasing? Everywhere. Everywhere on that interval. Now, this is a different situation, different equations. This is also possible. You could have a linear cost function, a quadratic revenue function, and you could then have a quadratic or maybe even a cubic profit function, but here your maximum profit doesn't happen at the highest number that you make. So your derivative will tell you where your 0 point is here. You take your derivative of your profit function. In this case, you'd find that you made your maximum profit about 420 computers. And if you make more than 420, you're going to start losing money. Either because your cost for making them has gone too high, or because you can't sell anymore. You've saturated the market, nobody else is buying. So in the one that we looked at, profit was always increasing, but realistically, most of the time it really looks like this. There is a place where you should stop making so many. So we'll talk a little bit about 13.2, and then I think we're going to call it a day. We've talked about increasing, we've talked about decreasing. Now we're going to go back and talk about something that you probably talked about in finite and algebra before, something about maximum points and minimum points. Okay? We're going to look at these mostly graphically, but remember that when you take a derivative, where the derivative is equal to 0, you've reached a maximum point, because that's where it goes from positive to negative on its slope, or when you've reached a minimum, it goes from negative to positive, so the derivative is going to be 0. And it's also going to be, potentially, there may be a place where there isn't a derivative, and yet there still could be a maximum or minimum, because you have a corner point, and the derivative doesn't exist. Relative maximums and minimums are talking about maximums and minimums only on a certain interval of the function. Only looking at a piece of the function, a certain group of x values. Absolute extrema, absolute maxes and mins means if you look at negative infinity to infinity, look over the whole domain of the function. So let's look at a graph and try to clarify the language. And really most of chapter 13 is about language. It's not really about calculus. Find all the intervals where this function has relative extrema, meaning maximums or minimums. Well, on the interval from negative infinity to x sub 1, do we have a relative maximum? Where is it? Since we don't actually know what that is, we'll just call it x sub 1, okay? On the interval from negative infinity to x sub 3, which is right here, do we also now have a relative minimum? Yes. In fact, we could say we have a relative minimum between x sub 1 and x sub 3, and it's at x sub 2. On the interval from x sub 2 up to but not including x sub 4, do we have a maximum? Do we have a relative maximum? From here, this is x sub 2, to here, this is x sub 4. Do we have a relative maximum? Yes. In fact, the slope of that function went from being positive, increasing, to negative, decreasing. But are we going to be able to find a derivative at x sub 3? Is the derivative defined at x sub 3? Why not? Why is there not a derivative of this function at x sub 3? It's a single sharp point. A single sharp point. It's not a smooth curve. So when you have a single sharp point, the problem that we run into is that I could draw a tangent line that way, or that way, or that way, or that way, or that way, and it doesn't have a unique tangent line. So even though I have a relative maximum on that interval from x sub 2 to x sub 4, the derivative doesn't exist at x sub 3 where that maximum point is. Is there a relative minimum between x sub 3 and positive infinity. What is it? It's at x sub 4. Now, is it possible for a function to have two maximums? No. It is not possible for a function to have two maximums. So even though this is a relative maximum, and this is a relative maximum, if I look at the interval from just below x sub 1 to just above x sub 4, the relative maximum is only that first one because it's higher. Is there an absolute maximum or minimum for this function? Think carefully. Over all of negative infinity to infinity, does this function have a maximum, an absolute maximum point or an absolute minimum point? No, why not? It's continuing to go up. Its end behavior is to positive infinity as you go to positive infinity in the domain, and it's negative infinity as you go to negative infinity in the domain. Okay? So in practice 1, identify all the x values of the points where that graph has relative extrema. And the solution to that is, well, at x sub 1, it decreases, comes to a minimum, and goes up. So that is a relative minimum point. At x sub 2, we have a relative maximum point. So between x sub 1 and x sub 3, we have a maximum. And then between 0 and infinity, we have a relative minimum, but not an absolute minimum. The relative minimum being from 0 to here. After that, it continues to go up further, so it only has a relative minimum. It doesn't have a relative maximum. In fact, this function does have an absolute minimum. Which one is it? X sub 1. That's the lowest it ever goes. It does not have an absolute maximum. And here again, that's that caution about x cubed. Don't think just because you have a critical point where the derivative is equal to 0 doesn't mean that it went from a max to a min. It could be going from an increasing to still increasing. So it may not be a max or a min. And there's that same graph again. So the whole idea of this section is that if you have a function that has a relative extremum at some point c, that means that c is a critical number in that function's domain, or it's an endpoint of the domain. It's where that function stops. So here's another cubic function where we've got it increasing, we reach a relative maximum. It's decreasing, we reach a relative minimum, and then it increases again forever. So it has one relative minimum, one relative maximum, but no absolute max or min, either one. And I'm going to skip over a lot of these because I don't know how much detail I'm going to go into on a test for chapter 13. So, graphing calculator method basically says that since we've got graphing calculators, we're not dinosaurs anymore, then you can use your graphing calculator in most cases to find your relative max and min. You don't really necessarily need to use the calculator to do any of that. When you use the calc menu, you can find its roots. The roots are your x-intercepts, and you can find your max and your min, and you can find your y-intercept for that matter. So we'll look at one application problem, and then I think we're going to call it a day. You have a company that manufactures and sells bicycles. The production managers determined that the cost and the demand functions for Q, as long as Q is equal to or greater than 0, bicycles, Q is the number of bicycles, is given by C of Q is equal to 10 plus 5Q plus 1 over 60Q to the third. And price is D of Q, which is 90 minus Q. And P is the price per bicycle. And they want us to find the maximum weekly revenue. How do you find revenue with the information that we have there? We've got a cost function and we've got a demand function based on price. How do you find revenue? What tells you your revenue? Revenue is how much per item when you sell it, right? And it's times how many items you sold, right? Okay, what else tells you how many you sold? Demand. For a given price, demand will tell you how many you sold. You just need to know the revenue. And this is the cost function and the demand function. So demand is how many are you going to sell? And then the price tells you how much you're going to sell each one for. So your revenue function is going to be P times 90, or excuse me, is going to be Q, which is the number of bicycles, times 90 minus Q, which is the price per bicycle. Does that make sense? Let's look at it on paper for a second. This is the demand function. This is how many you will sell at price P. Okay? P is in dollars. That's how many. How much each one sells for is P. Everybody good so far? Revenue is how many times how much. How many is the demand, D of Q. How much is the price, so here's your price per bicycle. Okay? Q is the number of bicycles. So there's your price, P, in dollars. Times Q, bicycles. So there's your revenue function. Your revenue function, notice, is in terms of Q, how many bicycles you sell. So there's your revenue function. And we want to find the maximum weekly revenue. In other words, we want to find our prime of Q and set it equal to 0, because that's when your revenue is at a maximum. It's when its derivative is just for one instant price, one instant number, it's going to be 0. The rate of change is going to be 0. So the derivative of 90Q is 90. And the derivative of Q squared is 2Q. What is that going to be equal to 0? It's going to be equal to 0 when Q is equal to 45. So your maximum revenue occurs when you sell 45 bicycles. Now it wants profit, the maximum weekly profit. Profit or I should say of Q, profit of Q bicycles is revenue minus cost. Here's your revenue. Here's your cost. And that is to the third power. Now that says to the third power there, but I think it's actually supposed to be second power. Let me look back on the PowerPoint. I think it's supposed to be second power. No, it says third power. Okay, we'll leave it third. So here's your profit function. Let's see. 90Q minus Q squared minus 10 minus 5Q minus 1 over 60 Q to the third. So let's put this in order. Negative 1 over 60 Q to the third minus Q squared. 90 minus 5 is 85Q minus 10. So here's your profit function. And again, it's revenue minus cost. So here's your profit function. And the profit function, while it's kind of ugly, is not hard to take the derivative of because it's all power rule. So find the maximum profit, P prime of Q, is equal to 3 times negative 160 is negative 3 over 60 Q squared minus 2Q plus 85. And you would want to set that equal to 0. And that'll tell you what value of Q gives you your maximum profit. And I think I'm going to make this a little bit simpler by multiplying the whole thing through by 60. So negative 3Q squared minus 60 times 2 is 120Q plus, I'm not going to do that one in my head, 5,100, okay, equals 0. Anybody want to factor that? Yeah, not me either. No, that's okay. What would you do to set this equal to 0 and find out what value of Q gives you your maximum profit? Quadratic formula. And one of these roots is going to be negative without a doubt, which you throw it away because it's of no use. One of them will be positive, so we would find the maximum profit and then find the price the company should charge to realize that profit. Well, once you've got Q, then you go back up here and plug it into the demand function and find out what price you need to be charging. Okay? To make the long story short, since we've only got about 8 minutes left and everybody wants to go home so you can study for your test. If you graph all of this, your maximum profit actually occurs where this is the widest. Because this is your cost function, this is your revenue function. So this actually is all revenue. Everything that's in that first part that's green is all revenue. And everything that's from here onward is loss. You're losing money because your costs are going up and your revenue's coming down because you're probably charging too much or you're spending too much. So your maximum profit is going to be when the greatest distance is between these two curves, and it actually turns out that it's about 27. It's about 27. So 27 bicycles, and then you can plug that in and find out what price you'll be charging for. Okay? Everybody ready to go home? Your eyes are glazing over. We're actually finished with chapter 13 at this point. I will give you a study guide for the next test after we finish this one. And for those people that didn't hear it yet, bring this with you on Tuesday. You will need it. You'll be allowed to use it on the test. And it's the only thing you're going to be allowed to use like a calculator. And this is your review for your test. And you have your test in your hands. Okay?
You keep saying that, so I'm gonna go with that. I was gonna ask you, I ain't gonna ask you. You gonna say this. I'm trying to get a clue. You might know, let me ever get a chance.